Greetings, welcome back. Still we are in session 3 and we are going to discuss the normal distribution. If you remember so far, we have spoken of how to write the hypotheses and categorize them in terms of null hypotheses or alternative hypotheses. We discussed the way that you need to actually consider the samples. When you take a look at the sample, the size, and all the attributes, you also need to basically list the variables, the independent variables, the dependent variables, the controlled variables between the samples that you're going to take in order to reject the null hypotheses or fail to reject the null hypotheses. You do have more than one sample, and you take a look at that, and basically you're going to have these samples have common factors involved. Those are supposed to be controlled variables. Obviously, you have an input, you have an output. Output depends on input, and these are the things that you need to come up with. And there is another aspects of the sample that we spoke of, and that is you always start from a small or simple sample, and then you ratchet up the complexity if the outcome is to reject the null hypotheses, and therefore you need to basically expand the number of variables that you have. So please review what I just said. These are the important elements of the scientific exploration, and without the proper questions, without the proper variables in mind, without the identification of dependency among the variables, you wouldn't start the experiment anyway. But generally speaking, we spoke of this basically taking the samples. I want to explain one form of the sample that we discuss, and we say normal distribution, has a normal distribution. I want to discuss that, and then I'm going to go, after this part is over, I will be going back again to the null hypotheses and alternative hypotheses and relate that to the curve that I'm about to discuss. So this part is, at this time, all that matters is that I want you to focus on the basically normal distribution function. Let's begin. This is an example. It's not entirely correct, but it helps me to explain what I mean. Imagine that these are the grades of the students from 0 all the way to 100. Let's assume that we are allowed to consider grades, discrete grades below 50. I understand that generally speaking, in any university environment, anything below 50 is simply considered F, for example. And in some universities, even anything below 60 is considered F, and they don't go into that area. But imagine you have basically a grade, a numerical grade, before you come to an alphabetical grade at the end of the day. What does this one say? It says that generally speaking, when you take a look at the performance of the students inside the class, you can see that a majority of the students are actually average performers. So you're going to have close to 68% of the students basically hitting the 50% mark, with 30%, 34% on the one side, the positive side, 34% on the negative side. Then we do have the high performers, and the high performers would be the one that are actually going to be in this area. They are going to go all the way from the numerical mark of 60 all the way to 100. Their numbers are not too many. There are some in every class who are extremely dedicated, who would basically do the projects, homework assignments, to spend time totally perhaps to some extent, and they want to achieve the best marks that they can in quizzes, midterm and final and everything else. And you could potentially see that there will be some 100%, 90% numerical values. At the same time, poor performance exists for a variety of reasons. There is no blame here, but I'm just saying about the numbers. There could be many reasons. It could be just COVID-19. It could be working outside to come up with the cash to pay for tuition fees. There are tons of reasons people may not have the best performance, including not much of an interest in the topic anyway. And you take a look at that, and this is going to be basically the area where the poor performers are going to be. This is the numerical grade, and this is the probability. And the way we calculate the basically probability is that, for example, we say 50. How many people got 50 out of 100? We realize that potentially, let's say you have a sample of 150 students. Let's assume you have a sample of 150 students, just for the sake of an argument. And then you realize after tallying all the grade that the number of people who got 50 marks, numerical marks, is 75 basically percent. So what is happening is that this is going to be 75 people, for example, or doesn't have to be 75. It's going to be the maximum that is going to be. For example, after the distributions is looked after, you could have the highest number of 50 at this point, and then a fewer number of 60 at this point, 55, 57 and everything, fewer number of 45, 47, 46. How do we calculate that? We pinpoint the number of people who got 50. Let's say 48 people got 50. And then we divide 48 by 150, the sample size. 48 divided by 150, the sample size. That's going to be what this sample is telling us to do. So this doesn't have to be 50. This is not necessarily 0.5. This could be the highest. And the highest could potentially be 0.3, 0.2, doesn't matter. But the way we calculated it is 48 divided by 150, and that's about, I think, if I may calculate that on my cell phone, I'm going to get 0.32. So 32% of students in this sample got exactly 50. And then there are other marks. Our marks are doesn't have to be necessarily integers. We have fractions, and we have 50.2, we have 50.3, we have 55, we have 59, 58, 58.66 perhaps, because it's fraction. And so basically we count the number of people who got that very specific grade. And we divide by the sample size, and we represent them on this graph. For example, if we take a look at this 80, and basically this might be 0.09, basically a vertical representation, which means only 9% got 80 mark in the class. And when we say 9% got 80 marks in the class, it means 9% out of 150. So I'm going to go and multiply by 150. That means 13.5 people got 80. We don't have half a people, so I just made up some number, and that's just what happened. So basically, in this case, this is supposed to be a very nice normal distribution. This is a curve that I want to explain. The belly of the curve is representative of the average performer, and then you are going to have the high performer, and then you have the poor performer. The reason that I said that this is not necessarily the true nature of a normal distribution, because the normal distribution function is actually a continuous function. This one is not continuous. If I wanted to just look into the grade itself, obviously there will be some empty spaces. Maybe you have 51.2 and then you have 55. You don't have anything in between, and that becomes empty. But on one argument, I could say this is analog, and this could potentially become basically continuous, because I could have 50.2, I could have 50.222, I could have 50.2259. I could have all of the values theoretically. So generally speaking, if you take a look at this, it's going to look like a bell curve. This is going to be looking at the bell curve. This curve has a number of properties. It has an average. This is called expected value. This is called mean of the signal. And this is often, this value 50 is often noted as mu in Greek letter, mu. Then obviously we do have a deviation from the center. And this deviation is going to be captured as one deviation, two deviations, three deviations, and so on. I'm going to show you in a curve in a moment. This one is numerical value. The vertical component of this curve is going to be the ratio. As I said, the number of people who got the 50 divided by the entire sample size. And then there is area under the curve. If you add the gray and the blue and the orange, and then the blue and the blue and the orange and the blue, sorry, this is dark blue, and then this one is going to be gray blue, all of that is going to be 1. What does that mean? It means that if you add them up, you are going to cover the entire sample. If you have 150 samples, this curve is supposed to capture all of the existing numerical grades in that sample pool. Now, when we said 150, we could argue this could be 2 million. We will talk about that in a moment, but at this time, having a very small sample, this is the beginning of what we call normal distribution. It has an average, it has a mean, mu, it has a standard deviation. A standard deviation, we discussed that in the remedial lectures to understand how to calculate the standard deviation. One sigma is called sigma, one sigma on this side, one sigma on this side, and that's 68%. So generally speaking, that's a huge portion of the class to be rotating around the center point. 68%, almost 70% of the class is actually centering around circling around the center point. With 2 sigma, you get 1 sigma here and 1 sigma here. Obviously, as you can see, the lengths, horizontal lengths is equal because they represent the sigma. With 2 sigma here and 2 sigma here, you capture 95%. That's huge. And then you have 3 sigma, and then you have 3 sigma, and then you have 4 and 5. And obviously, the more sigma you consider, the closer you would get to cover all of the area underneath of the normal curve, okay? Keep in mind that we are going to actually talk about these area under the curve, and this area under the curves are important for us to either accept a null hypothesis, reject a null hypothesis. So we will see. Accept a null hypothesis means fail to reject a null hypothesis. Okay, this is another look at the normal distribution. One more time, this is a mean. You have plus sigma, minus sigma, plus 2 sigma, minus 2 sigma, and so on. And this is the area underneath. So it says 0.14. It means from minus infinity to minus 3 sigma, this area is 0.14%. From minus 3 sigma up to minus 2 sigma, is going to be 2.14%. So this is the area. And as you can see, the majority, much of the area is actually circling around the center. Now, keep in mind, I said the center is 50, but that's not necessarily the case. I just wanted to use it as an example. Generally speaking, the center or the mean could be anything. It could even be 0 with negative numbers on one side and positive numbers on the other side. You could potentially claim that I'm going to shift the entire curve to the y-axis and then have everything on the negative side and everything on the positive side. It's symmetric in this one, just this one, it's symmetric. So this one is also symmetric, centering around the mean. And then there is a formula for this curve. It is a rather complex formula. You don't necessarily have to memorize it. It is available. 1 over underneath the fraction is sigma square root of 2 pi. Pi being 3.14. It's a beautiful number, as you know. E is an exponent, so E is 2.718. Again, your calculator has both pi and E to the power of, and if you take a look at the component on top, you have the x, and what does the x mean? X means from here to here, from here to here, from here to here. This is your x-axis, and this is your y-axis. This is your x-axis, and you could potentially tell me, and if you put the mean at 0, especially if you put the mean at 0, your x is going to be on the positive side, or x is going to be negative. You don't bring a negative sign to it. Inherently, it's going to be negative. So what do we have? We have x minus the mean to the power of 2, and the fraction underneath, you are going to have 2 sigma to the power of 2. So this formula is actually stressing the distance that the x is going to have compared to the center point. The center point speaks volume. 2 parameters are very important in this function. One parameter is going to be the mu, and the other one is going to be sigma. With mu and sigma, I could potentially draw this even with some estimate by hand. Calculators, you do have it, graphing tools available that could show you the continuous function. So I showed you a symmetrical normal distribution. And once again, I want to re-emphasize that, for example, in 1 sigma on the left and right, 68%, 2 sigma on the left and right, 95%, 3 sigma on the left and right, 99.7%. I just wanted to emphasize that. This is another view of this curve, very important curve. It is symmetric, as you can see. This is actually an indicative of sigma. So when we say 0 and 0.5, this is 0.5 sigma. This is 1 sigma. If you add 15 and 19, you get 34.1 basically percent on this one. And the blue area is the area underneath. The height of the curve is not supposed to be close to 1. It's not supposed to exceed 1. It's a very obvious understanding, because you're dividing by the sample size. If it is not divided by the sample size, then it's not normalized. If you want to normalize it, you divide it by the sample size, and this is going to be always less than 1. So keep that in mind. One thing you need to keep in mind, as we discuss the formula, this is mu and this is sigma, and it's going to have eventually an impact in how the curve is going to be seen. So if you take a look at that, that's mu. Mu is 2 positive, sigma is 1. So the curve is actually going to be here. Mu is equal to 2 and sigma is equal to 2. It means it's supposed to be wider. Mu is equal to -2, obviously it's going to be kind of a mirror here. And if you do -2, these two are going to be kind of a mirror over the y-axis. So using mu and sigma, you could potentially move them around. But the reality is, even class grade I was giving you as an example is not going to be symmetric. It's not going to look like a very nice symmetrical distributions. For example, in many classes, you will see that the mean is 85%, right? And then many people are on this side, and then there will be some people here, but this is going to be negative skewed. This is going to be positive skewed. The way you could potentially identify that, median, again, please refer to the remedial lecture. A median is less than the mean, median is more than the mean, and median and the mean are exactly the same. So these are different types of basically normal distributions. This is another reinforcement of the idea. Once again, the area underneath of the curve, and then the percentages representing the center and its deviation from the center, 1 a standard deviation, 2 a standard deviation, and so on. That's again, once again, this is a symmetric normal distribution, negatively skewed on the right and positively skewed on the left, okay? Here is the idea. if you take a look at this sample that I talked to, and I made it kind of neat and nice and symmetric just to be able to make my argument. So we have a class of 150 students just for the sake of an argument. And then you have 150 students inside, 150 grades inside. But you want to see the grade distributions, and you don't want to go through all of the papers, all of the records, all of the quizzes and everything else. You simply pick up 3 grades. And if you randomly pick up 3 grades, one of them could be here, one of them could be here that you picked up randomly, and one of them could be here. Can you see 3 components? Now, I might say, okay, 3 is too small. It's not indicative and conclusive. So I'm going to actually raise the number of samples. You said you have 150 students. Okay. I'm going to take 25 students. Now, depends on what you do. You could potentially get, for those 25 students you are about to experiment and collect and discuss and study, you may have 19 of them here. And then 6 of them are going to be on this side. 19 of them are going to be on this side, and 6 of them are going to be on this side. Once again, I want you to remember this shape, this skew. So what happened is that because you didn't reach the maximum sample allowed, which is 150, you could potentially be positively skewed on the left-hand side. Let's go back to this, and by accident, you could potentially pick up the 25 you did. Potentially 16 of them are going to be on this side in terms of the grade, numerical grade that you have just considered. And the rest, which would be 9 of them, are going to be on this side. Could be 1 here, and then a lot of gap, empty, and then some here, and then perhaps 5 of them are concentrated here. And then you can see 16 you said, so 7 of them here, and 2 of them are here, 1 of them here, you captured the good one. And then, so if you take a look at that, basically the sample you picked up from the original large bag of 150 students, you could potentially be here. So your 16 are here, and then your 9 are going to be on the other side. Do you follow me? So I have a huge basket of 150, and I only wanted to sample something. Now, if I ask you to increase the size of the sample, what happens? Let's say that you have 150 students in mind. This is your sample size. And then I'm asking you to do 125 samples out of 150. What do you think is going to look like? Let's pause for a moment. If you have 125 samples taken out of the biggest possibility, that 150, what do you think the sample is going to look like? Remember, my original sample, my original 150 student, the grade distribution looked like this. I know that. We did calculation, we put them on graph, everything is perfectly visualized the way you see it. Nothing is skewed, perfect, symmetric, right at the middle, 50%, above, below, numbers are there. Symmetric. But I'm asking you to get 125 samples out of this bag. Now, you're going to squeeze yourself. You're going to say 125. Okay, maybe I'm going to have 75 students here, and I'm going to have 50 here, 75 here, and 50 here. You don't have much choice to leave behind. You don't have much choice to leave behind. You can't see much of a gap between the samples you have, because what is happening is that you are forced to get close to the maximum number of entities inside the bag, which is 150. Let's try this one more time. This time, I'm going to ask you from the bag of 150 or this Excel sheet of 150 grades, I'm going to ask you to pick up 149 samples. 149 samples. So if you take a look at 149 samples, you seem to be just missing 1 sample. So if I ask you, can you tell me how the graph is going to look like? You're going to say it's going to look like exactly what you have, except that I have one empty here. And if you put 149 inside the bag and then take another 149 out of the bag, you may happen to have the empty bar at this point, but everything else is solid. Everything else is going to match exactly as I did in my first comprehensive analysis of my sample. Do you see what I'm trying to say? If the sample size you are trying to do is going to be 3, it is going to be skewed. It's going to be shifted on the left or the right. It's even, you may get lucky in a very extreme cases when you get 3, one of them is in the center and 2 of them are going to be exactly on the symmetric distance from the center. That would be a very strange and odd coincidence that you are going to give me a kind of a exactly as I have by just 3 samples. It's possible, but it's not happening quite often. Make sense? And if you increase the number of samples to 7, 25, 75, 80, 90, as you increase the number of samples, you are going to get closer and closer and closer to my graphic representation of the numerical values and everything else. This is one lesson to learn. The more sample you take, the closer you are going to be with the huge sample in terms of the mean and standard deviation, and even the shape. If you had 3, you could potentially be skewed. If you had 25, you could still be skewed. You go 75, you slowly look like normal distribution with some difficulties. You go on 120, I can see the normal distributions in your samples. You go 149, except the missing component, you look exactly like my graph. Your graph looks exactly like my graph. So that's the point. The very first lesson you need to keep in mind is that you need to keep in mind that when you increase the size of the samples, you are going to get closer and closer and closer to the solution space. We call it solution space, and the solution space in this case is going to be 150 students that I had in my class. That's the first thing I want you to keep in mind. Again, you could potentially have 10 samples, you could potentially have limited samples, but here is another point that I wanted to raise, and I partially raised just a moment ago. I said that if you pick up 10 samples out of my 150 solution population, solution space, you could put the 10 back in and take another one. It's going to actually shift a little bit here and there. You could put the 10 back in and grab another one. You could put 2 back in and grab 2 again. You could put 7 back in and grab 7 back, basically in place. What is happening? So if you are just interested to have 10 samples, there is another point that you need to keep in mind. Let's say that you're not going to raise your sample the way that this graph is showing. You are going to actually take a look at this graph is showing, this graph is showing, or perhaps as we discussed in the original graph, let's say we are not doing that. What we are going to do is simple. I'm going to take 7 sample out of the 150 being the solution space. I'm going to return the 7 sample back in and take another 7 and then put back in and another 7, put back in another 7 and do that. And each time I get 7 samples, I intentionally mentioned 7 to distinguish that from 150 and also to express the fact that it is very small sample. If you take the sample that I just asked you to do, 7, and then calculate the mean, there is going to be the mean. Perhaps you did 10 times and some of the means are going to happen on this side. And then you put them back in, by accident, you get close to the center point. And then you are going to see the sharp raise in my mean of the 7 sample. I'm just talking about 7. I'm not asking you to raise sample size. I'm asking you to keep the size of the sample fixed. Put it back in, grab in, put it back in, grab in. And then what happens is that you might actually hit closer to the center that I had. So, and that the center, as you can see, has the highest value, right? So if you go back, and I hope I can catch it, and you do this 10 times, you are going to record the mean of the 7 sample, fixed 7 sample, out of 150 samples, and you're going to record that. Now, let's repeat the same thing. Sample size is 7, and I'm going to do that 100 times. It's going to be basically more and more. I have a chance to capture the samples around the center point that I have. So this is my center point. And more, I'm going to capture the center point, basically sample, and it's going to actually capture it more and more. And if I do this with 1,000 times, what happens? 10,000 times, it's going to look a normal function itself. It's going to look like a normal function itself. This normal function is not necessarily this normal function. This normal function is generated by calculating the mean of fixed 7 sample. Now, as we said, as you can take a look, those 7 sample could be quite odd, strange looking, skewed. They could even be, perhaps because of the way you approach the sample, they could potentially have a different type of distribution approach. So basically here is one look at it. I'm looking at Bernoulli. You don't really need to know what Bernoulli is. And then as I increase the number of samples, I'm going to approach the normal distribution. One of the things that I need you to keep in mind is that irrespective of the type of distributions you're going to get, Bernoulli is actually 0 and 1, which means there is nothing, it's a kind of a digital, 0, 1. Poisson is going to be this shape, exponential is going to be this shape, U-shaped and uniform shape. And if you increase the number of samples you take, even from different types of distributions, it doesn't have to be normal distributions when you pick up your 7 samples. You could potentially pick the 7 sample, the 7 fixed sample that I ask you to do. It could potentially be uniform. You manage to make sure that the way you are going to select the points in my data set, you manage to pick them up in a uniform way. But as you increase the number of times you pick up 7 fixed sample out of 150, it's going to look like a normal distributions. I'm actually referring to different concepts. At one point, I said that if you have a sample of 15, 25, 75, 70, 120, 90, and then you had something like 140, 149, you will get closer and closer to this distribution. And this distribution happens to be normal distribution. It doesn't have to be normal distribution. It could be skewed normal distributions. It could be any different shape with 150 samples that I have. In this approach, I'm asking you to raise the number of samples. Whatever this looks like, and it doesn't have to be normal distribution, whatever it looks like, even a skewed distribution, even the one that is supposed to be shown here, right, such as this one, as you increase the number of size, the size of your sample from 10, 15, 20, 80, 120, 130, 140, 149, you are going to get closer and closer and closer to my actual sample behavior. That's one lesson I need you to learn. The other lesson I'm asking you to learn is that if you repeat an experiment, and in this case, my sample size is 7, and I never changed it, and all I did was to take the average of the sample size and then put the average here. This is always going to be normal distributions. Even though your shape is going to be, your distribution is not normal distributions. It's not normal distribution. If every time you pick up 7 samples using whatever distribution you have in mind, and you repeat that 1,000 times, 10,000 times, and everything else, the mean of that is going to actually go and form a normal distribution. This is another way of looking at it. You have normal, uniform, skewed, general, anything, doesn't matter. And you're going to have repeated your approach to the experiment twice or 30 times. As you can see, 30 times is going to look more and more like a normal distribution. This normal distribution is not the same as the distribution of your population. Your population could be normal, it could be uniform, it could be skewed, it could be anything, general. But then as we repeat the experiment and we take the mean of the samples, and the sample size could be 2,000. And I'm going to explain that in a moment in terms of election. So that's what is going to happen. Once again, you have uniform, it becomes perhaps narrow, normal distribution. Bimodal, again, you have it. Skewed, you have it. Similar to normal, again, you're going to have it. This one, the endpoint normal function, normal result is not the same as the actual normal distributions of your solution space, your population. I need you to keep in mind, these two are two different lessons that I need you to keep in mind, okay? This is another way of looking at it, once again, to reinforce the understanding. You go here, this is the sample you got, you take the average, you put it here, 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 and then what happens is that these averages are going to look like a normal distribution. This is called central limit theorem. Central limit theorem. And we want to basically keep that in mind, okay? Now, in terms of election, we spoke of election in the past. Let's close this class by discussing the election. Now, if I wanted to, what is my population? My population or solution space is going to be potentially 190 million people who are eligible to vote. Make sense? So I can't ask all of them. This is insane. It's impractical. Besides, people change their mind, and their mind, what matters their mind is when they cast the ballot. That's what matters, not the mind that they had 10 weeks ago, 2 months ago, 1 week ago. That doesn't matter. So you don't want to do that. It's waste of resource. So what you do, you're going to pick up 2,000 people and call them election polling. And you're going to ask them who they are going to vote, candidate X, candidate Y. Obviously, that's a point of debate, whether this question is the right question to ask or not. But you have 2,000, and you do this 2,000 by news station A, news station B, news station C, institution D, institution E, F, H, G, whatever you call. All of these institutions come in, and they have their own 2,000 people to take sample of, 2,400 maybe. They don't even have agreed on the number of size of the sample itself. Some of them to 2,400, some of them 2,000, some of them just 1,000. But the idea is, if you repeat this over and over and over again, you are going to actually get to the final outcome with the which is going to tell you what's going to happen, right? So you're going to, this is supposed to look like a normal distribution. So I need you to keep that in mind. Another thing you could potentially say is that if my population of 190 million people are eligible to vote, as I try to capture 2,000 and 2,000 and 2,000, I'm actually going to capture some of the 2,000 here. You could be in an irregular space. You could be in an area that is highly Republican. You could be sampling in an area that is highly Democrats or independent, and therefore your results are going to be skewed. So this is just an example, but of course the skewed is going to be better, right? So with that in mind, what is happening is that you want to capture the spirit of this data set. And it's like flashing a light in a dark room. So you go in a dark room, you are blindfolded, you enter into the room, the doors are closed, it's completely blocked from outside, it's completely dark, but it's not a typical cube room that you know, as in living space. The question you're supposed to answer is, can you tell me what this room looks like? And the way you're going to do, you're going to take the flashlight and you're going to put the flashlight onto the ceiling, onto the walls, and perhaps onto the floor. And each time you're going to grab the data by visualizing, by basically getting the information from through the input of eye from the sight. And then this is like DJ. So the light comes in, you see something, you don't see something, you see something, you don't see something. And eventually, if you repeat that many, many times, the room is going to look clear to you, even if it is dark. You can potentially say, you know how the room looks like. Where is desk? Where is DJ? Where are the people who are dancing on the floor? You could potentially say, where is the glass of water? Who is serving and who is not? You see what I mean? So that's the concept of sampling. I try to explain that, and this is just for the sake of basically an example. As I said, we don't have necessarily everything nice and clean. We don't necessarily have even the normal distributions in our population, and depends on that. All we have to hope for is, first and foremost, take more and more and more samples in order to identify what the room looks like, in order to identify what the sentiment of the population is when they want to do a vote. And there are many questions you need to bring to the table: the age group, the education, the race, possibly the location, geography, the preferences at the moment. Maybe I'm a Democrat, but because I like a policy of person X, I'm going to vote for person X, and so on. So those are the secondary things. We started from a simple polling, and that is, who are you voting? And we said person X, person B, and person Y. It is extremely simple. And then that is going to be giving us some results. And perhaps when we take a look at the news outlets, we realize something is not right. Some of the samples are actually rejecting the notion that person X is going to win the election. And then you are going to say, hey, listen, you asked the wrong question. You invaded the privacy of the person you are asking the question from. You are intrusive. And the question you ask is not appropriate. Besides, you didn't consider the education, the age, the geography, the income, the aspiration, the goals, objectives that the person has. And altogether, it becomes a secondary, basically, polling. And hopefully, with the clear mindset and secondary polling, you'll get better and better and better results. Election polling, just to close the argument, has not necessarily been accurate in the past. They may have been accurate when they wanted to talk about popular vote, they may, and that's a point of debate. But in terms of electoral college, they may not have been able to successfully predict what it is in some of the occasions. For example, in the past election, one of the candidates got about 75 million. The other candidates got about 81 million. Obviously, when you compare the 75 million, no one in the polling came close to 75 million. And there are question marks on why the polling didn't get to 75 million marks. And these are an open question for the community. As a data scientist, you need to ask those questions and you need to basically come with an answer. I hope I was able to express to you what the normal distribution is and the type of normal distributions we have, and the expectation in terms of sample size and its relationship with the solution space. And I hope you remember that as we are going to go into the next stage of the class. Still, this is session 3, part 2. Thank you.